Yellow. Today we're going to be doing our Unit 7 review for IB Precalc HL. Unit 7 is our polar and complex unit, so we're going to be going over topics such as polar convergence, graphing polar graphs, solving for polar and common points, polar lines in their normal forms, complex numbers and their special arithmetics, and complex roots. Let's get started. So the first thing that we're going to do is polar convergence. Since we know that a polar point can be graphed as r comma theta, we're going to want to convert r comma theta into x and y coordinates. So in order to do that, we have these conversions on the left. We have r is equal to the square root of x squared plus y squared. It's just the Pythagorean theorem. Theta is equal to inverse tan y over x, just to get the angle from the origin to the point. This would be theta over here. And x is equal to r cosine theta, and y is equal to sine theta. So with this in knowledge, we can begin to really get into some of these problems. So for our first problem, we're going to want to convert r is equal to 3 sine theta into a rectangular form, which is Cartesian form, or just x and y. So our first step is to be getting rid of this r right here. So in order to get rid of it, our first, counterintuitively, our first step would actually be to multiply by r on both sides. So we get r squared is equal to r times 3 sine theta. And notice how x, or y actually, is equal to r times sine theta. This correlates, so we can just group that together. R squared is equal to 3r sine theta. And then we can cancel that out into r squared is equal to 3x, or 3y, sorry. And then from there, we can, since we have r and r squared, we can get, substitute r squared in for x squared plus y squared is equal to 3y. And you could just stop there if you wanted to, because you already have it in just x and y. But if you wanted to convert it even further, you can use completing the square for like a quadratic in order to get your final answer. But I'm not going to do that. It takes too much time. Another example when you want to use polar conversions is converting from rectangular form into polar coordinates or polar equations. So here we would want to convert x is equal to 2 into polar. This one's also pretty straightforward, honestly. We can just take this and set that to equal to r. Change the colors. R cosine theta is equal to 2. And you're basically done. You can just do r is equal to 2 over cosine theta. And then if you want to keep it looking nice, you can do r is equal to secant theta. And that's how you solve those two. But we also have a little bit harder stuff that you might see on an IB problem set. Or, yeah, we have this. R is equal to 4 cosine 2 theta. This one's a little bit harder and requires a little bit more math to do. So the first thing we want to do is notice this cosine 2 theta and think back to our unit 6, in which we have trig identities. We can convert that cosine 2 theta into our trig identity. R is equal to 4 parentheses cosine squared theta minus sine squared theta. That would be our first step. And then our second step would be thinking back to the last page where we had x is equal to r cosine theta. And we can kind of manipulate that to x over r is equal to cosine theta. And then we can make it mirror what we want even more. getting it to x over r squared is equal to cosine squared theta. So now that we have that, we can substitute that in. R is equal to 4x over r squared minus, and the same principle applies to sine squared, y over r squared. From here, we can just kind of distribute it out. R is equal to 4x squared over r squared minus 4y squared over r squared. I think you can see where we go from here. Multiply both sides by r squared. R to the r cubed is equal to 4x squared minus y squared. And since we know what r is, we can just put that here. Square root, it's running out of space actually. X squared plus y squared to the power of 3 is equal to 4x squared minus 4y squared. I forgot the 4 over here. But there, that would be our final answer over here. Move it over here, make it big. Maybe I color it in a different color too. Color it in pink. Yeah, why not? Color all that in pink. Very cool. So that would be our answer for that one. It's a little bit harder, but you can still get the concept if you remember our trig identities from before. So yeah, these on the left side, these are all our new identities we're introducing, but it's also important to remember our trig identities, and this is just some practice. The next thing to know is graphing polar and how to graph a polar equation, or knowing what the different graphs are. From this list, it is important to notice that I excluded two very important graphs, circle graph, and a spiral graph. A spiral graph is just r is equal to theta. As you increase theta, the radius increases, and that's why it looks like a big spiral going on forever. Pretty self-explanatory. And the other one would be a simple circle graph. There's two ways you can get a circle. You just have r equal to a set radius. And so it's just on the plane, it would just look like a big circle with a set radius of 4. Or you can also have r is equal to cosine theta. And it would just kind of look like a circle just off to the side like that. And you can manipulate it too as well, like negative cosine, it'd be on the other side, stuff like that. But it's nothing too deep, and that's why I decided not to include it. The ones that are a little bit more complex, the rose, the limaçon, and the lemon skate, are a little bit different and a little bit harder. So let's start off with the rose. Rose, they have the equation is r is equal to a sine n theta, or r is equal to cosine n theta, where a is the max length of each petal. So if you wanted to have a petal with a length of 4 units, you would set a equal to 4, and n would be the number of petals. But an important thing to note for roses is that if n is odd, then the number of petals is equal to n. But if n is even, then the number of petals is equal to 2n. So you can see here I have two rose graphs, pretty simple rose graphs. I think this one is equal to, r is equal to 2 sine 2 theta, and this one's r is equal to 2 sine cosine theta. And the way that I know that is because at theta is equal to 0, sine will never be any value. It'll always be 0. So at theta is equal to 0, which would be at this position, it'll be over here, and that's why it starts over there, versus cosine at theta is equal to 0, which would be the positive x-axis. It would have a value, and that's why it looks like that. And another reason why I know it's n is equal to 2 instead of n is equal to 4 is because it has double the petals, so 2 is half of 4, and that's why it would have that many petals. The next graph that is important to know about is the limacon. It's the cardioid. It kind of looks like a weird heart, I guess. That's like a really bad off the riff limacon. But yeah, you get what I'm trying to say. There's the equation is r is equal to a plus b sine theta, or r is equal to a plus b cosine theta. Where some important rules to know is that if the absolute value of a is less than b, then the limacon becomes an inner loop, which kind of has a graph that looks like this and is very distinct. If a is equal to b, it's just a normal limacon called a cardioid, and it has like a distinct punch there, and this point, or like this, the pointed part of the limacon will be at 0, 0, which is really useful to know in order to identify what type of limacon it is just from looking at it. And if you have a is greater than b, then it'll be a dimpled limacon. So to start off, I have a graph of an interloop limacon. We can see here that our a value of 2 is obviously less than 3, and that's why we have a dimpled limacon. And since it's a cosine, it'll be in the direction of right and left on the x-axis. If it were a sine limacon, then it would be up and down, just because. The next limacon would be a cardioid. You can see how I was talking about earlier, that little pointed part of the limacon is at 0, 0, and the fact that these two, the a and b values, are the same. Another thing to also actually point out about limacon is their max radius that they'll get to is a plus b. So you can see 2 plus 3 is equal to 5, and you can see the farthest out this limacon would get to is x is equal to 5. And then it's the same thing with this one. Since 2 plus 2 is equal to 4, the max radius this one gets out to is 4. And our last limacon, a dimpled limacon, we got 3 is bigger than 5 over 2, which is 2.5. And we can see that it has a little dimple, but it doesn't exactly reach the origin. And that the max radius it gets to is, 5.5. Yes, it does get to 5.5. And the last thing is I have over here for graphing polar is the lemon skate. It's kind of a weird graph. It's r squared is equal to a squared, where a is the length of the petal is equal to sine 2 theta, and r is equal to a squared cosine 2 theta. They're kind of weird. I think the main thing about lemon skates is you being able to identify what the graph is. So this one down here, it just looks like the infinity symbol. It's a basic lemon skate. This one is r squared is equal to 4 cosine 2 theta. And you can see that the length of this petal is 2, as the max it gets to is over here is 2. And since that's 2 squared is equal to 4, that's why we have the 4 there. And something very similarly to how the roses work, cosine lemon skates, they have the petal on the x-axis because cosine is able to have actual positive values there. But if we look at this sine lemon skate, you can see that it tries to avoid the x-axis, and because it's an r squared, it'll also try to avoid the y-axis as well, and that's why it's on the diagonal. Solving for common points. Oh, this is lovely. Well, since we're able to graph polar, we're also going to be wanting to solve for polar systems of equations. So if we were to try to regularly solve this, we can see that r is equal to 4 and r is also equal to 4 cosine 2 theta. We can just probably just substitute 4 for r. And that would be a very straightforward way into getting into this. Cosine 2 theta. We can divide by 4 on both sides. 1 is equal to cosine 2 theta. Multiply by inverse cosine on both sides. Cos negative 1 of 1 is equal to 2 theta. Cosine of 1 is equal to 0. Well, inverse cosine of 1 is equal to 0. 0 is equal to 2 theta plus, oh yeah, don't forget that we're solving on the interval of 0 to theta to 2 pi. We're solving on that interval. And so this would be plus 2 pi for all solutions. We divide by 2 on both sides. 0 is equal to theta plus pi. And so however many times we want to go around the theta loop, the answer is always going to be pi times. Let's see if we try to graph that. We're not going to get all the answers we want, but we get some of the answers we want. So right here, the solutions that we're getting out of it would be 0 and pi, because that's the only ones that fit in our range of 0 to 2 pi. But we can see that graphing that, we're missing out on some stuff. Yeah. We have r is equal to 4 right here. That's the basic circle. Now what I'm going to do is graph in red is the points of 4 cosine 2 theta, which is a rose, if you remember from the last slide. Now let's do the whole 2 pi thing, graph some points up to 2 pi. So if we start with theta is equal to 0, cosine of 0 is equal to 1, 1 times 4 is 4. Since theta of 0 is over here, and 4 away, we get there. Our first intersection, we'd expect that if theta is equal to 0, that's one of the solutions we're anticipating. If we go to pi over 4, which is just good to check, pi over 4 times 2 is equal to pi over 2. Cosine of pi over 2 is equal to 0. 4 times 0 is 0, so we get a point over here. If we go to pi over half times 2 is equal to pi. Cosine of pi is equal to negative 1. Negative 1 times 4 is negative 4, and that's why we get a point over here. Since pi over 2 is over here, but we want to go to negative 4, we go to the opposite side. If we were continued this pattern, because I know it's a very long pattern, we would end up getting a rose that looks like this, right? And as you can see, we're missing some points from our answer, particularly over here and over here. That's not in our answer. That is at pi and 2 pi. So we know our intersection points here would be 4, 0, and 4 pi. But looking at this, we can also realize our intersection points might be negative 4 pi over half and negative 4 3 pi over half. Sorry, I blanked over there. Those would be our common points. The answers beginning in negative 4, because we don't see them solving through algebra. We can only see them through graphing. And also part of the reason why they're common points is because solving through algebra, we don't typically expect getting points directly on top of each other. So that was like an easy example of that. I have a harder example to try out, but I'm actually really lazy and don't want to do it. But you get the gist. You have to be able to graph these equations effectively in order to find all the solutions instead of just half of them, what you usually get. Up next, we're kind of jumping out around a little bit. We get polar lines and how we convert a line into polar. So if we want to convert this green line into polar, we'd want to first find its normal and the angle that it creates. The distance away that the closest point to the line is to the origin would be P. This is also the tangent line because it would create a 90-degree angle with the line we're trying to look for. And we would also have phi, which is the angle that the normal line creates with the positive x-axis. And you can see over here we have the steps in order to find or convert our polar line or our line into polar. So we can start off with, I forget what these do. Yeah, okay. We can start off over here, and we can try to find the polar equation of this line to the nearest whole. So the first thing is we want to convert to normal, as I was saying, and the way we do that is we divide the entire equation by the magnitude. So we can start by doing 3 squared plus negative 1 squared is the magnitude, and we get 9 plus 1 root 10, okay? We got root 10 there. So our new equation here would be 3x minus y equals 1 over root 10 over root 10 over root 10. Next step is find the angle using the coefficients. We can see that, and by what I mean by that is we want to see inverse cosine of 3 over root 10 is equal to our phi value. And since this is not on our unit circle, nobody's expecting us to have this memorized, but we can use our calculator to find this out. 3 over square root 10. Load radians. Let's put this into, oh, it's asking it for degrees, but I'm using my calculator right here. But we want to double check and find out which quadrant this is in. We can see that the point 3, negative 1 is in the fourth quadrant. We're going to want an answer in the fourth quadrant. So it would be useful to use sine in this case. Sine 3 over root 10. Is our answer? Oh, we actually wouldn't get any. So we got our phi value of 342 because we're rounding. 342 degrees. So that would be our phi value. Let me just move this up. And we're halfway there. And the last step is to find the P and convert it fully into polar equation, which has, actually I should have mentioned this earlier, which looks like this. R cosine theta minus phi is equal to P, or R is equal to P over cosine theta minus phi. It's the same thing, just restructured depending on what your teacher is asking for. But since we have our phi value and we know that our P value is just this on the other side of the equation, so P is equal to 1 over root 10, we can say that our equation is R cosine theta minus 342 degrees is equal to 1 over root 10. There we go. That's our answer. And since we're rounding phi to the nearest whole number, that's pretty much our answer. That's all we got. purple. We have another equation. Instead, we're starting off with a polar equation, and we want to convert it into a rectangular form. So let's convert this to something that more recognizable, at least for me. Let's do r cosine theta minus pi over half is equal to 14. This is pretty easy to recognize. Our phi value is equal to pi over half, and our p value is equal to 14. And so we can just plug it back into what we wanted. So we could do cosine of pi over half x plus sine pi over half y is equal to, and I also made a little bit of a mistake in my notation. It's a small mistake, but we're almost there. So we left off saying that cosine, just converting all this into coefficients. Cosine pi over 2 is equal to 0, and sine pi over 2 is equal to 1. So we get y is equal to 14, and that would actually be our answer. I don't know where I was going. I was leading myself onto nowhere. But that would be our final answer for that question. And looking at the other question, do you see how we converted it? In both ways, from Cartesian to polar and polar to Cartesian. Next, we have a little bit more complex stuff using complex numbers. So for complex numbers, we would have a complex point, z, that's how we denote a complex point, is equal to x plus yi. In this case, where y is equal to the imaginary plane, y represents the imaginary number line, or we can also denote it as r cosine theta plus I sine theta. Oh, there should be a parentheses there. I was tweaking about that. There should be a parentheses here. But yeah, r times cosine theta plus I sine theta. Or we can also combine the cosine and the I sine, because it's a lot to write out as cis theta, r cis theta. And so over here on this side, we would want to just practice converting from complex into polar, or yeah, complex notation into polar notation, and polar notation back into complex notation. So for this one, you would want to convert from this polar form to complex. First thing we might want to do is expand out this into 40 times cosine 5 pi over 6 plus I sine, oh, my pen's bugging out, 5 pi over 6. Then we can just solve for that because those are just numbers. Z equals to 40 times cosine of 5 pi over 6 is equal to negative root 3 over 2 plus I 1/2 times 1/2. Need a parentheses there. And then just to tidy all that up, we get negative 20 root 3 plus 20i. And that would be our point in Cartesian form, or Argon form, because we're using imaginary, so it would be on the Argon plane. But that would be our answer there. Let's use another ugly color to highlight that. And then our next problem, practice problem, we would just be doing the same exact thing, except converting from Argon form or Cartesian form back into polar. So first we want to remember from our slide 2 that theta is equal to the inverse tan of x over y. We have, oh, that's the wrong slide. We have right here our x and our y, so we can do theta is equal to 10, negative 1, negative 12 over 5. And I have a feeling this is not going to be a nice number, although this is a triangle in which you could solve for the hypotenuse if you wanted to, since the hypotenuse of this triangle would be 13. Forget what you call it. Now, this would be, again, in the fourth quadrant, as we had in our last problem, and I got from the calculator negative 67.380 is equal to our theta. Because I'm too lazy to convert that back into degrees, we'll just stick with that. And we want our magnitude, which we can, or R, which we can remember is just the Pythagorean theorem, so 5 squared plus 12 squared. That I was telling you is somewhat regular and easy to memorize, which is 13. So if we just shrink all that scrap work into the corner so we can get our final answer, we would get our final answer of Z is equal to 13 cis negative 67.380 as our final answer for that. Pretty cool if you ask me. Pretty simple as well. A little bit of work, but not too bad. Now, the next thing about the complex unit, as I was saying before on slide 1, is special arithmetic you can do with these complex coordinates. And that goes into our next topic a little bit too. So, given that we have our coordinate, our first coordinate, z1 is equal to r1 cis theta of 1, and our second coordinate, which is the same thing, if we were to try to find the sum of these two coordinates, it would have this equation. Z1 times Z2 is equal to R1 times R2 times cis theta 1 plus theta 2. And if we're trying to find the quotient of these 2 points, Z1 over Z2, it would be equal to R1 over R2 times cis 1 theta 1 minus theta 2. And the last one, the one that we use in our next topic the most, Z to the power of n is equal to R to the power of n times cis theta times n. So if to write this one out, because this one can be a little bit confusing, if we had Z to the second is equal to R to the second cis to theta. And that's how you would find that. And I know in this year's semester B review, we had a couple problems like that, and in our challenge problems as well. Now, if we were to want to try and practice that, we would have this. Using our special arithmetic, given W is equal to negative root 2 over 2 plus root 2 over 2I, find W to the fourth. Now, this is in Argon form, or rectangular form, whatever you want to call it. So we're going to need to convert this into polar interval in order to use our special arithmetic that I mentioned over here. And in this case, we'd be using the last one. So what we would do is convert this into polar. So theta. So we have that answer. And we also need the magnitude, which is really easy to find. We just do 1 over root 2 squared plus 1 over root 2 squared. Imagine there's a parentheses. That's all. Oh, I'm being a bit slow there. That's just 1. Radius is equal to 1. So since we have that, we can just convert that into polar as r, no, wait, what the heck? Z is equal to cis 3 pi over 4th, and, or actually in this case, W. Sorry. W is equal to 6 cis 3 pi over 4. And since we want W to the 4th, W to the 4th is equal to 1 to the 4th times cis 3 pi over 4 times 4. We're almost done. W to the 4th is equal to cis, because 1 to the 4th is still 1, cis 3 pi. And if we want to convert that, that's a pretty good answer. We can also say simplify this to cis pi, since we want it to remain in a reasonable domain of 0 to 2 pi. And if we convert that back into Cartesian or rectangular, we get W is equal to, what is that? -1 plus 0i. Yep. So that's how you would do that. That's how you apply the special arithmetic that comes with complex numbers and converting them from polar to nonpolar using this. Now the last thing that we got to do that I absolutely dread is De Moivre's theorem and finding complex roots. So what does it mean to find a complex root? Well, we want to see what to the 3rd power is equal to 8i. So we're just trying to find the complex point that multiplied by itself 3 times would be equal to 8i. Now, this generally comes fairly simply. We just have to use De Moivre's theorem to say that z is equal to r over 1 to the n, blah, 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 blah. It's a lot of stuff. Let me just show you how to do it. So if we take this, we would do z is equal to, we would just convert z to the 3rd into some equation that we can use to apply and find r cis z to the 3rd is equal to cis 3 theta. Because z to the 3rd, we can just convert that into its polar form to make it easier for us to find. We can also use our special arithmetic to find that. And we'd also want to convert this into polar form. This one is actually pretty self-explanatory. Cis, because it lies on pi over 2. Because it lies on the positive complex axis, we would get pi over 2. Now, the thing here we can notice is some of these terms correspond to each other. R to the 3rd corresponds to this 8 here, and this 3 times theta corresponds to this pi over 2. So we can use that to our advantage and isolate certain values that we want to find. R cubed is equal to 8, so that means just cube root that, r is equal to 2. And if we do 3 theta is equal to pi over 2, divide by 3, we got pi over 6 is equal to theta. So if we combine that into one final point that we can use, we can say the cube root of 8i would be 2 cis pi over 6. Now, if you want to convert that into polar form to find a more satisfying answer to you, be my guest. But honestly, I could not be bothered. We can use this same process to find more roots. For example, am I forgetting something? Oh, yes, this is numbers. So there's actually multiple numbers. This pi over 6 actually came with a little bit of a friend. This would be 2, that would be 2k pi over plus 2k pi. And since we divided by 3 on this side, it would be over 3. And over here, we would have k includes 0, 1, and 2. So if we would add 2 pi over thirds, no, if we would have our solutions of pi over 6 plus 2 pi thirds, and then pi over 6 plus 4 pi thirds, those would be our 3 solutions to the problem. Actually, I can write them out. Z equal to cis pi over 6 z1 z2 is equal to 2 cis pi over 6 plus 2 pi thirds, and z3, sorry, equal to 2 cis pi over 6 plus 4 pi thirds. And those would be your answers. Those would be your 3 numbers that if you were to try to cube them, they would all have the same answer of 8i. We can use this again to find, which is de Moivre's theorem, to find the 4 roots of z is equal to 5 cis pi over 3 theta. So we start off with assuming that this is a 4th root, z. So we can do z to the 4th is equal to 5 cis pi over 3. And now using de Moivre's theorem, we can just 4th root all of them. So this entire thing, 5 cis pi over 3, is to the 4th root, or to the 4th root. And we can use the special arithmetic found on this slide to help us out with that. So now we have, I think I'm running out of space, z is equal to 5 to the 1/4 times cis 1/4 times pi over 3. And then we get that 2k pi over n as well. We can't forget about that. Just let me move this all over so I give myself some more space to work and you guys some more space to learn and see what I'm talking about. That over there works. Why not? Let me erase this so it's more legible. My handwriting is getting really sloppy. Z is equal to 5 to the 1/4 times cis pi over 3 over 4 plus 2k pi over 4. And in this case, because we have the 4th root, we have k is equal to, k includes 0, 1, 2, and 3, because we want n minus 1 solutions. So we had put that actually over here just to serve as a reminder for us. Now if we finish this off finally, z is equal to 4 root 5. I'm not trying to find out what that is. Cis pi over 12 plus k pi over half. So our four solutions, z1 is equal to 4 root 5 cis pi over 12, because we can start with k is equal to 0. Z2 is equal to 4 root 5 cis pi over 12 plus 1/2. Well, actually, I'm kind of lazy. I could have just done the math myself. That would be 7 pi over 12. I'm running out of space, really. Z2 is equal to 4 root 5 cis pi over 12 plus 1. Oh, not plus 1/2, plus pi over half. So this one would be plus pi. And that's 3. What the heck? Z to the fourth point, that would get you this answer. Oh my lord. I had no space. Pi over 12 plus 3 pi over 2. That would be your last solution. So yeah, this has been a pretty long summary of Unit 7 and everything that we learned in it, or everything useful that we learned in it. Going from polar conversions, graphing polar conversions again, this time into complex. What was this? Polar lines, common points, and then finally roots. Hope you all enjoy. Hope you guys do on whatever test you guys are taking, and I'll see y'all later.